Hello everyone. Thank you for attending this seminar. This is track one for Powering the Future Summit, organized by IEEE Power and Energy Society Young Professionals. Our distinguished guest speaker is Dr. ZQ Zhu. He is a professor in Department of and Electrical Engineering at University of Sheffield, UK, and head of Electrical Machine and Drive Research Group. Dr. Zhu is also a Fellow of Royal Academy of Engineering, IEEE Fellow, and IET Fellow. Thank you, Professor Zhu, for presenting your research or working with industries on renewable energy and electrification. IEEE Industry Applications Society is also partnering in this session. Thank you also Professor Wenjin Li, who is the IAS President, for supporting this session. There is a presentation. Participants can leave questions in the chat box and it will be addressed after the presentation. Dr. Zhu, you can start your presentation now.
Thank you. Hello. Good afternoon from the University of Sheffield. I'm ZQ Zhu. It's my pleasure to give this presentation on impact, working with industries on renewable energy and electrification. As you know, impact has become more and more important. Even in the IEEE Fellow nomination, now it is required to cite 2 individual contributions with the impact and also evidence of the impact. For Royal Academy of Engineering Fellowship in the United Kingdom, one of the engineering excellency criteria is also about the impact. For any academic and research institute, in addition to providing evidence of a successful academic career, you need to provide and identify the innovation or invention which result in successful commercial products. So first of all, I would like to share my specialty with you. My specialty actually is on electrical machines and the control system. Very often people think it is an older discipline. Yes, it is 200 years with innovations. It has been very widely applied in different market sectors. That is why a lot of people think the basic theories maybe have already well developed, but I'll show you later, okay? But first of all, I would like to show you 2 pioneers in the United Kingdom. First is Faraday. He developed the induction law, which is the foundation for all electrical machines. And then Maxwell, he developed a unified theory for electromagnetism. In fact, if you go back and look at the history of innovation in electrical machines, permanent magnet machine was the first invented in 1831, and 10 years later, switch reluctance machine was invented. Only until 1888, induction machine was invented by Tesla. This is Tesla. So you may be aware that I'm the winner of Nikola Tesla Award this year. It is after his name. But you know, now we also have another Tesla, which is a car, is an electric vehicle, commercialized electric vehicle. So I just would like to show you Dawson's innovation technologies. And as an example, just to illustrate that motors are still in revolution or evolution. In fact, in all Dawson's products, inside is a high-speed motor, which has, can achieve 100,000 RPM. And then together with the aerodynamic design, as a lot of other innovative design. For example, in the vacuum cleaner, this is the first without the dust bag. And then in the hair dryer and also hand dryer, there's no blades, no blades, real physical blade, but the air blades. And then in the fan, there's no blades as well. And then for the handheld vacuum cleaner, it's wireless. So all those machines rely on the high-speed motor. I just would like to give you an idea how fast this motor is. And if you have a motor connected to the main power supply, in the United Kingdom is 50 hertz. So the motor normally can only operate maximum at 3,000 RPM. But this machine is 100,000 RPM because as the speed increases, then the power increases. So for the same power, you can reduce the size, make it lighter. In fact, in all those domestic appliances, you can see the first generation, the color is yellow. Inside is a single-phase switched reluctance machine. And then now the second generation is purple-colored or gray-colored. Inside is a high-speed, single-phase permanent magnet motor. So still there's a lot of innovations continuing. Now, what I would like to talk about is the layers permanent magnet machine. And Sheffield, we have a UK leading engineering faculty. And Sheffield actually is a global leader in the permanent magnet machine research and development. And in fact, the permanent magnet machines have the highest efficiency among all type of machines, electrical machines. Usually when we talk about the permanent magnet machines, it is a layers magnet, particularly neodymium boron magnet. In this case, China has a majority of global layers material for neodymium boron magnet, and typically is about 60%. But in terms of the magnet itself, I'm sure is more than 80%. However, neodymium boron magnet was invented by General Motors and Sumitomo simultaneously in 1984. Now, I would like to introduce a very basic permanent magnet machine. A permanent machine, that means it uses permanent magnet for excitation. Inside, you're able to find the permanent magnet, you can see there, and also the copper to carry the current in order to produce torque. And also you have the iron to improve the magnet circuit. Now in any type of machine, we also have a stator, which is stationary, and a rotor rotating. This actually is a closed session for the Toyota Prius. Okay, this is a rotor. You can see here, this is a stator. And in fact, all this type of machine, we only have three type of materials. This is also why I very often talk with a student, electrical engineer for machine design, really a great chef can cook food, but that food is a product. So we can cook millions of products, yeah, and from the three materials. So we are great electrical engineers. And I would like to show you one example. For example, the rotor for the permanent magnet machine. There's loads there, and here I illustrate some of them, but due to the time limit, I wasn't able to go through one by one. So what we're really doing, if you're very talented, you can apply your talent to develop and also identify the most appropriate machine topologies for a specific application. For example, for the offshore one power, direct drive one power generators, we prefer to use the surface-mounted magnet rotor. And then if you are working in the domestic appliances, we usually employ a technique so-called frictional slot machine. And then you very often will go for this kind of rotor topology. However, for electric vehicle, and no matter whether it's a Toyota Prius or Nissan or BMW or Tesla, we are using a type of machine which is called the RPM machine, interior permanent magnet rotor. And inside this type of machine, we can utilize so-called reluctance torque, so that for the same torque, we can reduce the amount of permanent magnet. In all those applications, because the cost is very sensitive, therefore, we try to minimize the number of magnets per pole. And in this case, you can see for Toyota Prius, we only got 2 magnets per pole. And Nissan Leaf got 3 magnets per pole. And BMW got 2 magnets per pole. And this one got 4 magnets per pole. Because if you reduce the number of magnets, you can reduce the amount of magnets, but also save the manufacturing cost because you have less magnets to handle. And here shows a special type of so-called Halbeck machine. Inside the magnetization is self-shaded. It has been in mass production in Toyota's iLeo, and this technology was developed by Sheffield, for example. And I would like to continue with electric vehicle application. For that, we have the basic requirements. We require high torque at a low speed and high power at a high speed so that you can start the car very quickly off the street with high acceleration. And also you can drive very fast to take over other cars. And on the motorway, for example, if you want to take other car, then you need that kind of performance. But currently, due to the limit of battery energy, it is even more important to have a high efficiency region, wide as possible, particularly towards the low speed and the light torque as well. However, there's a mismatch between machine high efficiency region and also the most frequently operated region for electric vehicles. Here, low speed and low torque and also high speed. So there's a mismatch there. This is still a big challenge. Now, I would like to show you a typical driving cycle and then map this driving cycle in the torque speed region for an electric machine. And the cross represents the operating point. So if you see more cross points, that means the electric vehicle is more frequently operated in that region. And my student has optimized a lot of different machine technologies, including induction machine, synchronous reluctance machine, and the permanent magnet machine, but using ferrite or using neodymium barium magnet or using mixed ferrite and the neodymium barium magnet, and compared with Toyota Prius machine. Now, in this case, we applied this driving cycle. As you can see, the efficiency, as long as you put the magnet inside the machine, no matter whether it's a ferrite or neodymium barium magnet, and the system efficiency will be higher than those non-magnet machines by 10 to 15% at least. In this case, you can see the induction machine, no matter whether it's a copper cage or aluminum cage or synchronous reluctance machine, the efficiency are relatively low. That is illustrate why currently for electric vehicle, permanent magnet machines are most widely used. Even for Tesla, initially they started with the induction machine. Now they also have employed permanent magnet machines as well because of the high efficiency. Because of the excellent performance of permanent magnet machine, which, for example, high torque density, high power density, and high efficiency, they are widely applied to different market sectors. For example, aerospace, electric vehicle, and automation, servo systems, and warm power generation, and domestic appliances, for example, lawnmower, vacuum cleaner, and the washing machine, and the power steering. So I'm quite sure all of you are using permanent magnet motors in one or another way. However, the global in terms of global challenges, now it's towards zero net and also circular economy. And for that, in electrical engineering, we are working in renewable energy and electrification. In fact, I just would like to tell you one simple story. One day I traveled from Edinburgh to Sheffield. Then my neighbor sitting next to me, he's also from Sheffield. And then he asked me, what do you do? What's your specialty? Then I just thought, if I told him I'm working on electrical machines or permanent magnet machines, he might don't know at all. So I told him I'm working on warm power generation and electric vehicle. Then his response immediately, oh, you work on high tech. Yes, indeed, we are working on high tech, research. So I would like to show you examples about my work with industry. And first of all, would like to introduce electrical machines and drives research group at the University of Sheffield. We have 14 faculty members, including 8 full professors with complementary skill. We have more than 100 PhD and postdoctors, and it is a global leader in the research and the development of permanent magnet machines and control systems. We are very proud of that because we have very strong industry collaborations, which is evidenced by the fact that we host 6 industry-funded research centers, including Rolls-Royce, Siemens, CRC, which is a fast train, Meidi Group. We also host 3 government-funded platforms, including EPSRC funded Prosperity Partnership on offshore wind. EPSRC funded the Future Electrical Machines Manufacturing Hub, and also Offshore Renewable Energy Catapult on powertrain research. And by the way, I got a simple map here. Sheffield is here. It's the east side of Manchester, and then to north of London by train takes 2 hours only. And I just would like to share also my research field since I joined Sheffield. I've been at Sheffield for 33 years. I first would like to mention that in each market sector, I usually only work with one company to make my life easier for the IP and also confidentiality. Therefore, for the wind power, I only work with Siemens. Okay, for domestic appliance, I only work with Meidi Group. For electrified transportation, there's a lot of supermarket sectors there. For electric vehicle, therefore, for hybrid electric vehicle, I work with Toyota. For pure electric vehicle, I work with Nissan. For mild hybrid electric vehicle, I work with Value. For hub motor, I work with Protein. And then for power steering, work with ZF and Bros. Then for more electric aircraft, I work with Rolls-Royce. For fast train propulsion, I work with CRC. But I also would like to share the landscape of Sheffield. Sheffield was the capital of steel and iron in the 18th century. In fact, it is the only relatively large city in the UK which is adjacent to the national park, which is called the Peak District National Park. You can see that's the view. In fact, this is a foggy, not very sunshiny day, and very nice. And this is Chatsworth House. It's a very famous house in the Peak District. And this is the one that I talked recently. In fact, the one in the middle, which is at the back of my garden. So every day I can see this type of view. You know, I think this probably explains not only the motor and my specialty, but also because the environment attracted me to stay here for 33 years. I think I'm going to stay here for the rest of my life as well. Okay, now I will start with a story how I started to work with Toyota Group, Emerald Europe UK Research Center. In fact, I started my cooperation with Toyota Group via a very small consultant project about 20 years ago. At that time, they requested me to do actually is just a paperwork, a literature review for high-speed motors. So I spent 1 month, and I didn't do any other job, just dedicated myself on reviewing this because I really enjoyed reading those papers as well. So I produced a report, and to be honest, I'm very happy with the report. I didn't publish anything until now, but I did shoot a couple of my students, for example. But in theory, at that time, after I completed, I can just email to this company. But I learned the company. I said, I like to come to talk slow about the report. And then I hired a car and booked the hotel all by myself at my own expenses, then went there. So we go through all those reports, and the company is also very happy. Then towards the end, the general manager said, wow, Professor Zhu, actually we are working on hundreds of thousand RPM high-speed motor. And but unfortunately, we got problem. We jammed there for quite a long time now. And would you like to have a look? And then I said, oh, yes, of course, I'll be delighted to have a look. So we went to the laboratory, and then they showed me this current waveform. To be honest, initially I was very confident to identify the problem because during my own PhD period, I analyzed the current waveform for brushed DC permanent magnet motor very well, much in depth. But when I saw that, that's a bit weird. I never see a waveform like this anyway. But I realized that they have the pit berm there. So I suggested to the engineer, can you please remove the pit berm? Then the engineer told me, no, you can't. You're not allowed because this is a high-speed motor. If you take the pit berm off, that may got an accident, because it will operate even higher speed than cause accident. But then I said, no, it's no problem because you can take the pit berm post-width modulation off, but control it by hand. You can use the hand to control the supplied voltage. This is why you can see here, the voltage here is about 120 volt. Then the voltage has been reduced to less than 100 volt when you take off the pit berm. Then with this current waveform, then I know what's the problem. So I told them, you got problem there. What's the problem? You don't have any problem with the motor. You don't have any problem with the controller. However, you have the problem about matching of the controller and the motor. Why? Because I have done the analysis before by myself, and you can see these two motor designs. Okay, it's a 2-pole 3-slot, very simple. But then for brushed DC operation, this is a typical waveform there. Then what we're doing is high speed. We detect the zero correction of this phase or terminal voltage. This got a 0 point there. So we detected that, and then to find the rotor position. However, if you design a motor like this, you don't have the zero correction because this one uses less turns, this one uses more turns. The inductance here is low. This one inductance is higher. Consequently, this one got a low diode conducting angle. This one got a high diode conducting. The conducting angle actually is from this point right to that point. When it is more than 30 degrees, you lost the zero correction. Then it's not suitable anymore for zero detecting. In fact, not only the analysis I have done before that, but I also have 2 prototypes made. One is suitable for sensorless, one is not suitable for sensorless, has been operated at 130,000 RPM successfully. You can see here, this one got a very nice close point there. That's a terminal voltage, phase voltage or terminal voltage. But this one, you don't have the terminal voltage. So how I can operate at 130,000 RPM? Because I use a Hall sensor. It's not sensitive. So it's great. My experience is very simple. Sometimes you cooperate with the industry. We are working in the university. We need to push the technology at least one step ahead. Then you can serve the industry. And in fact, since then, I have been working with them for 21 years continuously. And we developed a lot of ultra-high speed motors, more than 100,000 RPM. We developed novel Halbach permanent magnet machines and developed the state PM machines, particularly switched flux machines, and also variable flux machines, including memory machines, as well as the linear motors with resonant actuators. All those joint research put us ahead, as a leading position in those R&D. And also, not only that, we also have 9 granted patents, and it's used in the mass-produced products. We have several mass-produced products there. And also, we have published a lot of joint papers and also win 4 Best Paper Award as well. This is a photo in 2010. I visited the Asian Sakis headquarters, which is one of 4 major groups in Toyota. I delivered a seminar, and then afterwards we took a photo here. So this was in Japan. And I also have 12 years cooperation with Nissan. Now the cooperation with Nissan is different from Toyota because all the cooperation is via joint Nissan and also UK government funded project. And so I worked with them on 3 major projects. And the first one is ultra efficient electrical machine and the drives for electric vehicle. And then the second one is integrated propulsion and the charge system for plug-in electric vehicle. And then currently we still work on a high torque electric vehicle motor. And as you know, if you work on the project by government, not necessarily the government can guarantee you the continuity. So during that gap, then Nissan directly funded my project from Japan. So this is the photo in 2010. I visited Tokyo and their headquarters as well as their research center, but I'm not allowed to take any photo inside. That's why the photo was taken from outside. And wow, this is Nissan Leaf was initially put into the market. So I had a test ride outside their technology center in Cranfield in the United Kingdom. And this is the photo with Valeo in France. And so I met the advanced engineering manager in Tokyo as well. Then they funded me the first project with 2 PhDs. And then the second project with 3 PhDs. And then the third one also with 3 PhDs. And you know, my talk today is more focused on permanent magnet machines, but it's very interesting. They requested me to work on induction machines. Okay, I wasn't able to talk in detail, but I did a very successful as well, and in cooperation with them. And so in Valeo, they call me Mr. Induction Machines. And here I would like to introduce Rolls-Royce University Technology Center in Advanced Electrical Machines. Rolls-Royce, they selected the best group globally on electrical machines. So they select us, so it's a great honor. The center was established in 2003 and currently directed by my colleague, Professor Zhu, and mainly focus on electrical system for aerospace gas turbines. And we aim to develop high reliable and fault-tolerant high torque power density generators and systems. And as you know, in for a large aircraft, in the future, it needs 1 megawatt power on board. So you can't use the cable supply the power from the land to the aircraft. Otherwise, if the aircraft, flying around the world, you need to have the cable for how long? Yeah. And then the power is usually generated on board next to the engine. But you know the engine got a high temperature. For example, at the low pressure stage, the environmental temperature is 150 degrees. Even at a high pressure stage, is about 250 degrees above. And so in this case, the temperature is several times higher than we normally design the machine. So in that case, any development, you really need to wash your mind, wash your head, and to consider the electromagnetic performance of the material and the mechanical performance. For example, even the losses may be 4 or 5 times higher than the normal machine, And so we need to take this in consideration. And I just would like to mention that in Sheffield, what we operate is we have this center, for example, but I also involved as well. And this is a photo which was taken after the project at Rolls-Royce. And of course, the project, everything, all the activities will be coordinated by the director, Professor Zhu. Then I'm the helper. And whenever required, then I'll participate into the research project. And then for my other centers, exactly the same. So now I'll move on to Siemens One Power. Siemens One Power, actually, their headquarters is in Denmark. And the project actually started, I tried to get to the original why it started. So in 2003, I gave a seminar organized by UK Magnetic Society. In fact, my presentation is on the permanent magnet brush DC motor for vacuum cleaner, which is based on the PhD thesis my PhD student work on, and in fact finished about 3 years before that. So I give a presentation, and then inside essentially talk about vacuum cleaner, and then the maximum speed is 20,000 RPM. And then original one was power driven by universal motor. So we developed the three-phase and also single-phase permanent magnet motors. Look at the different inverter, and then look at the electromagnetic interference, and of course the efficiency, as well as the cost noise as well. But I just would like to say at that time we didn't cooperate with any industry, so we bought that vacuum cleaner from the shop. Okay, but during that presentation, there's one person was sitting there. That's Jan here. Yeah. So it's from Grundfos in Denmark. And Grundfos is very famous for pump. You can go back at home and have a look at your central heating pump. If it is made by Grundfos, then it must be a very high quality one. Okay, so what they would like me to do is to develop high-speed, low-cost permanent magnet motors and drive systems for them. But there's a limit. The time needed to be only 6 months. So it's a very short, a very challenge. So what we did is during that 6 months, and my student and I, we worked together, and we delivered two sets of motor and the drive, including motor and the drive. One is three-phase motor, and the other one is a single-phase motor. So here shows the measured waveform and the no load and also load. This photo was taken in the laboratory at Sheffield. And later, at the end of the project, I need to travel there and get tested in their laboratory. But because the confidential, I wasn't allowed to take a photo. So this is the result taken at the Sheffield. And also the single-phase motor as well, and including the drive and the motor, successfully operated at the no load and high and the load at the required speed as well. So it has been very successful. So consequently, I was invited to give a seminar in the company as well. Then afterwards, this is a photo was taken. I would like to mention that, and Jan, my industry partner and the project manager, and because the project is very successful, so he was promoted from project manager to department manager, later on promoted to vice president and also senior vice president in the company. What I would like to say is when you cooperate with a company, you know, if you did a good job, then your collaborator will be happy, his boss will be happy, and his boss's boss also will be happy. So this is very important. So we need to try our best, to make the project successful. So this is a very good example. Now, important thing is he later also he told me, and his CEO was so happy. So mentioned to all members in the company and said, we should learn from Sheffield. We should learn from ZQ Zhu for the high quality of research, for deliver in time as well. So why I can do that? Important thing is I have quite a lot of experience because as I mentioned, I worked on the vacuum cleaner for 20,000 RPM. I have been also working on 120,000 RPM motor, okay, for uranium pump and for the garden tool, for example. And also we have a lot of experience not only in electromagnetics, but also the mechanical aspect as well. This is why we can deliver, right? If I have worked on 120,000 RPM motor, of course I can deliver for the 45,000 RPM type of prototype. Of course, this is three-phase type. There's some challenge there. But for three-phase one, I have worked on 20,000 RPM one. Of course, their requirement is higher than this, right? But it's very important, we have worked one step in advance, then to serve the industry. But important, the industry also provide a lot of challenges to us. Then we solve the problem. So form a, very good circle there. And now, what I would like to, why I'm saying this, because in 2008, there's one person actually here, Kurt. He moved from Grundfos to Siemens One Power, and then in charge of the generator development. So the first thing he did is contact me because he heard from his colleague and also his boss and about the work we did. In fact, I didn't know him at that time, and he come to see us. In fact, before that, we have never worked on one power, no experience at all. But he told me, well, your group, you have the experience working for aerospace. For aerospace, the reliability is very important. We are going to work on the offshore wind power. The reliability is very important, but we'll never ever to exceed the aerospace. But you also have a lot of experience working in electric vehicle. And then for electric vehicle, the cost is very important, right? And then for our wind power, low cost is also important, but it's not as demand for electric vehicle. So he strongly believes, and also his colleagues strongly believe, we have the strength. In fact, we have the knowledge in different market sectors. There's no competition. And then the experience will be very useful for the wind power. So they trust us. They think we can do it. But we did it. And you can see here, this is a photo when we established the center. And this is a photo in 10 years anniversary. I'll show you another photo later. And maybe you'll be interested that, well, he is our vice president of the university, and that's me. You can see that the major difference about me. So after 10 years, my hair changed from black to a lot of gray hair. But my PhD student at that time, Dr. Owen Thomas, he hasn't changed at all. He was the first Siemens engineer in the center. And I'm very pleased to witness, he grew up from a fresh graduate to a very mature senior manager in the Siemens Gamesa group. And as I mentioned, 2 years ago, we celebrated the 10 years anniversary of the center because it has been very successful. As I mentioned, not only the technology side is successful, not only the collaboration is successful, but I'm very pleased, our graduates, our students also, become an important manager in the company, grow up there, and, gain the experience based on this platform. So this is important. And this center, the senior vice president he's there, and he commented that this center is Siemens' global model for cooperation with universities. This is really a high praise, And why comment on that? Because we have the research impact. As I mentioned, the impact is important, not only just the writing papers. We have been working together with Siemens Gamesa and helped in innovative direct drive offshore wind power generator development. So this is a new technology, right? And also we have helped to successfully develop and also commercialize 5 generations of turbine with power from 3 megawatt to 14 megawatt. Yeah, with numerous orders as well. And it was a lot of money. Yeah, so this is a new product. And also we helped the Siemens Gamesa become the #1 provider for the global offshore wind facilities because they provide more than 70% of the generator systems and has incorporated our research via direct collaboration and also employ our graduates. And at the moment, there's 2 managers there, and 50% of the key engineers are from our group. So by working together, we have doubled our strength by working together. So that's very important. I just quickly show you a couple of examples here. This is the first ever direct drive turbine, a 3 megawatt one developed for onshore. Of course, you can use it for offshore, but at that time, specifically designed for onshore. And you can see how big they are. There's somebody there, right? And importantly, there's no gearbox. Okay, so it's very reliable. Now, this is the 6 megawatt one, which is specifically designed for offshore. Yeah, and this has been sold in larger quantities as well. And then the latest one is 14 megawatt. It's huge, honestly. It will be in series production in 2020. I'm sure we will be able to produce that well before that. Yeah. And this one, if you look at the diameter of the rotor here, which is 222 meters, and the swapped area is equivalent to 5.5 standard football pitches. So it's huge, can collect loads of wind energy. And actually, above the tower, that head there is 500 tons. So there's a lot of engineering work, very challenge, makes success, very good there. And next, I would like to very briefly talk about our cooperation with CRC and also METI Group. And at the Sheffield, we have a CRC Electric Drives Technology Research Center. CRC is the global leader in fast train propulsion development and also commercialization. So our cooperation actually started by a research project in 2013. Actually, was introduced to me by UK government's Trade and Commercial Department. And after 1 year, we established a research center. We aim to develop the key technologies for next generation of fast train propulsion based on permanent magnet machines and the control system. Because currently the fast train is driven by induction machines. And so the CTO in the company in CRC, he has a vision, would like to replace the induction machine systems by permanent machine system because it is more efficient, it is quieter, it is more comfortable. And so I'm always very proud, when you go to China and sit on the fast train, it's fantastic technology, very fast, very comfortable, vibration is very, very low. So I just would like to remind you, there's a research center at Sheffield, funded by them. And for METI Group, and we also have electrical motors and control systems under this center. In fact, I helped them to establish a research center in 2011 in Shanghai. And then we have another research center at Sheffield in 2017. I am the adjunct director, and that since 2010. And since that time, we have a lot of joint research project and at Sheffield, funded by the METI Group. And we mainly work on motors, drives, and control systems for domestic appliances, and of course now have been extended. And here choose a couple photos. This is the time when the center was established in Shanghai, and essentially started from nothing, only myself, one person, and then now in 2019 we have that many people. In fact, we have a lot more people now, and because they recently experienced a significant expansion. And this is a photo was taken with the CEO of METI Group, and because at that time when I heard that I was elected as a fellow of Royal Academy of Engineering, at that time I was visiting the company as well. So, and we have taken a photo, and this is a photo when the vice VP and also CTO of METI Group come to Sheffield, and together with our vice president and also head of the department. And now for this one, I just would like to talk a little bit more detail about the research impact. And the important thing again is a new product. First, we developed numerous innovative motor control products for the domestic appliance. Essentially, we have applied the permanent magnet motors to permanent magnetize all those domestic appliances and then integrate into their 300 million motors per annum. That's why we can add the revenue of the groups. And then we also developed a lot of techniques, not only revolutionized the existing product, but also into the industrial automation, for example. And then that enabling technology provided them the confidence in acquire that KUKA and the Servotronic. KUKA, the robot, industrial robots. And METI Group is owner. It's owned by METI Group, KUKA, okay? By the way, METI Group currently is Global Fortune 288. So it is a larger company. And obviously, we have working together in the motors and the drive systems. We have expanded the product from domestic appliances and also to automation and then automotive components and the industrial drives as well. And even more important is the talented technologist. So 3 of my ex-PhD students, they are now junior managers in the group. And also there's a dozen of my ex-PhD students that become the key R&D engineers or managers in the company. We have been working on a lot of products. So here I just would like to show you one example, and it's a intelligent washing machine. So in this washing machine, first of all, the technology for this washing machine is even more challenging than one power generator, even more challenging than electric vehicle. Why? Because inside it also uses the sensorless technology, but you have the heavy load to start with because you have closed water inside. But for one power, sensorless starting is very easy. You have the one just blow it, and then it will start to rotate. Yeah? But for this one, it's very challenging. Then it's even more challenging than electric vehicle because for electric vehicle propulsion, the maximum speed to base speed, the ratio is about 3. But inside of the washing machine, for dryer and washing, the speed is 30 times. So it's 10 times more challenge. And in addition to that, we also have embodied a lot of intelligent technology. For example, this washing machine can weight how much clothes you have put into the washing machine, then decide how much washing powder should be. And also can decide whether the clothes has been jammed to the side, because in that case it will create an unbalanced magnetic force, then create the vibration and also the noise. Then we can, using the motor control, all-wire motor control, and then more uniformly distributed. So it has been very successful in mass production. So this center now, this year is also 10 years as well. So it has been very successful. And the University of Sheffield has put the Siemens case and also this case as 2 research impact cases submitted to the UK government. And in our Faculty of Engineering, we only have 11. So they have selected 2 of my cooperation with industries as UK government research impact cases. And of course, you might say that, well, you work so much with industry, and then how about your research with the government? So I would like to show you some examples here. The first one is EPSRC funded the Prosperity Partnership on offshore wind power. The project is called a new partnership on offshore wind. And in fact, it involves with 3 universities, Sheffield, including my group, and also a group in mechanical engineering, Durham University, Hull University. Then industry partners include the Siemens Gamesa and Ørsted. Ørsted is the largest wind farm developer in the world. Siemens is the largest offshore wind facility provider in the world as well. And it is a 5-year project, 7.6 million pounds. This is a photo was taken 2 years ago for our research, but there are all the researchers participating in that project. If you're interested, you're also welcome to look at our website here as well, and for more details. And in this project, essentially, we try to forge a partnership, working together, essentially, try to reduce the cost of energy. So how to reduce the cost of energy? First of all, we need to increase the annual energy production, and then try to reduce the capital expenditure, as well as the operation and the maintenance expenditure as well. Then how to achieve this? By 4 work packages, including generator and converters, blades and also foundation, as well as structural health monitoring of the blades, and condition monitoring, and also fault tolerance. And this, for all those work packages, led by both industry and academics. Okay, and we also have an EPSRC funded the Future Electrical Machines Manufacturing Hub, and it totals 28 million pounds. EPSRC funded directly 10 million pounds. It is directed by my colleague, Professor Galanjo. He is also the director of the Rolls-Royce University Technology Center. And my colleague, Professor Jiabing Wang, he did a fantastic work yeah, and also very well known globally. And my colleague Grant is here, and then myself is here. We are the co-members in that. And this project is led by Sheffield. And we also hosted the offshore renewable energy powertrain research hub. And this is funded by Offshore Renewable Energy Catapult and directed by my colleague David Stone. He's here, yeah, and myself here. We also have colleagues from mechanical engineering as well there. So we are working together. And also, I would like to show you some technologies in electrical machines. You know, as I mentioned, it has been 200 years. Still, there's a lot of new technologies there, but I will only show you one example. And about the field modulation and also magnetic geared machines. This concept, and we pioneered in the world. And a lot of ideas actually developed at the University of Sheffield. And here I put the year down. This is when the paper was first published. In fact, this is a magnetic gear, and this is a magnetic geared machine. Were developed by my colleague, Professor Kees Atalak. He's a very talented research. And so IEEE PES government funded the project. Here is a magnetic gear. And now they are extensively investigated globally. For magnetic gear, essentially you have 3 parts. Yeah, one rotated faster, one rotated slower, and then have a modulator there. Okay, and then this type of magnetic gear, you don't need to worry about the overload because only just a slip, not like a mechanical gear, it will be jammed there. You don't need to have a lubricants, for example. But then my colleague Kees Atalak also has applied that concept into the machine. So it is a magnetic geared machine. This is only just one example. You can expand that to a variety of machines. Now extensively investigated globally. And this shows the very first magnetic gear. Okay, this side and that side, actually there's this side and that side, there's no coupling, mechanical coupling, but you can see the speed here is different from that side. Yeah. And also this is my keynote speech, one of the PowerPoint, okay, during my keynote speech in 2014 at RCMS. And this summarizes the relationship with the magnetic gear principle and a variety of machine topologies. In fact, all the machines can be grouped into there, as I presented at the conference. So essentially what you can see here, this is a magnetic gear, this is a magnetic gear, but this has some different. In this case, the modulator is stationary, and then the magnet parts, they are rotating at the opposite direction. And then in this one magnet part is fixed, then modulator and another part of magnet, they are rotating. Now, let's have a look at the first one first. The most important concept here is any multi-phase windings can produce a rotating field. So in that case, we have used the 3-phase. Of course, you can use 5-phase or this. And the 3-phase mimic that rotating magnet part there. Therefore, it becomes like this. There's nothing else changed. Only that part replaced by a conventional, like a stator of the conventional electrical machine. Then, in this case, this is a machine. And now, what do you notice here is you have 2 air gaps there. That modulator is stationary. This is stationary, although the field is rotating. So you can remove the air gap to simplify this one, to make it only 1 air gap. Yeah, 1 air gap. So you stick those iron pieces on the top of there. Then become a single air gap, 1 stator, 1 rotor. Yeah, exactly like a conventional machine. But in this case, this is called a vernier machine because it got field modulation and the magnetic geared principle embodied there. This is one example. You can expand that to other type of machines as well. And this is one of the hot research spots at the moment globally. And then in this case, it's the same. We apply multi-3-phase stator to replace the rotating magnet parts there. They end up like that. So end up with 2 stators. Yeah, this is a stator, this is a stator, and 1 rotor. So it's a double stator, 1 rotor machine. Okay, like that. And of course, you can have the magnet this side or that side, it doesn't matter because originally that is a magnet there as well. So you have a variety of combination there. Important thing is this is not a rotor. This is a stator. In fact, you can move that stator to the embodied with that stator. Try to reduce the air gap from 2 to 1. Okay, that become more conventional machine. More conventional machine. This is called a switched flux machine or flux switching machine. Again, there's a larger group into that family. So all those machines at the Sheffield, we are leading the research globally. And I've said a lot of research and that's a cooperation. I just would like to highlight some of my personal achievement. Maybe you say that, oh, you work with industry, then how about your research? So I have published 1,300 papers, including more than 500 IEEE transition papers and IET proceeding papers. This number actually is the number one in the field of electrical machines. And then the papers are very widely cited. That make it globally number two in the field of electrical machines. The number one is Professor Tom Lipple. And according to the Stanford University at the end of last year, and they ranked the researchers in the world according to the C-score. I'm also here. Yeah. In fact, those above me, they are all specializing on power electronics. Okay, so I'm the person in electromagnetic, in the electrical machines, and well, I'm honored, next to all those famous professors. Yeah. And Professor Lipple is also there. Professor Fred Lee, he is a pioneer in power electronics, for example. And wow, and in 2009, I was elected as an IEEE fellow. Then in 2016, I was elected as a fellow of Royal Academy of Engineering due to my impact cooperation with industry. And then in 2019, I won the IEEE Industrial Application Society's Outstanding Achievement Award. And then this year, when the IEEE Nikola Tesla Award for my contributions to the design, modeling, control, and application of AC permanent mega machines and the drives. So this is a medal. And at the back of that, with my name on it. Yeah, and I'm very honored. So the last one, I would like to finish to share a photo with you. This photo was taken 2 years ago. At that time, our research center with Siemens is almost 10 years. Okay, so Siemens has specifically arranged me to travel to Denmark and then get on the top of the tower, one turbine tower there. There's 6 of them there, and all of them are 6 megawatt one, developed for offshore wind power application. But because they are the first batch for offshore wind power, so it has been installed onshore just in case. But I can very pleased to report to you they've been successful operating ever since. And this photo was taken when I was there. Okay, this is more than 100 meters high. You can see a lot of people standing there. I'm sure Dr. Owen Thomas is also there. But the photo was taken when I was standing here, take the photo. I used my mobile phone, take that photo. Yeah. And so this is a 6 megawatt direct drive, permanent magnet generators for offshore wind power application. To be honest, I just would like to share my feeling at the time. When I take this photo, I feel really proud of myself because, I'm a university professor and we are able to help the industries to realize their dreams. And meanwhile, we are able also to realize our dreams. And then in addition, we have provided excellent platforms for the student, to become managers and key R&D researchers. So this is really fantastic. Meanwhile, we also can contribute to the global zero net and also circular economies. This is fantastic. So I really would like to encourage you, to involve with electrical engineering, study for electrical engineering, and also join us to work on this fascinating research field. Thank you very much.
Thank you, Professor Zhu, again for the presentation. We have several questions. but we run out of time. Let me ask one question to you, and you can also see it in the chat box. So, dear Professor Zhu, in your opinion, how will the limit of rare earth and neodymium magnet product around the world affect the EV electric vehicle industry and magnet-based motor design in long-term planning?
Well, in long-term planning, a lot of people worried because the layers material dominated by China, and then there's a limit of the resources as well. And so in my personal opinion, in short term, permanent magnet machines will still dominate in the electric vehicle is because the limit of the battery energy. And then in long term, I don't think I need to worry about it too much as well, because first of all, at the moment, outside of China, at least as far as I understand, we're doing extensive research for the on those so-called non-layers magnet technology. And in fact, a lot of them already applied into the electric vehicle. For example, like a Nissan, and they use much less layers material in their motor already. And also, a lot of people working on like a magnetless machine. This one you can interpret it two ways. One is use less layers magnet, another one get rid of the layers magnet. So there's a lot of research activity going on as well. But don't forget, Tesla started with induction machine. In my personal opinion, at the moment, the best non-magnet machine is the induction machine. But hopefully at that time, the battery will be fine, the life, and also, everything will be fine.
Okay, thank you for the reply. So we will have a breakout session following this meeting for networking with all participants. We will also do some quiz in breakout session based on Professor Zhu's presentation. You may get some small prize. See you soon in the breakout session. And thank you again, Professor Zhu, for the excellent presentation. Yeah.
Thank you. Okay, I think it is. Shall I pick up the questions, or will you provide it to me?
Hi, sir. We will send you all the questions, and we will collect the answers from you and post it in the social medias for you. Is that okay?
Yeah. So if I click, sorry, I didn't share my screen, so it wouldn't come. Okay. Here, so shall I read out that in your opinion, will the motor design such as the asymmetric PMSM with higher power density compared with the conventional PMSM gain more importance in future electric vehicle? Well, this is a very specific one. I think I followed up with my invited speaker to the Magnetic Society about this session. Well, asymmetric PM permanent magnet machines can have high torque with the same amount of layers magnet. That's important. So it can reduce and improve the torque density. And so it can apply. Important things, a lot of people also worried as well, because when I initially talk with some companies, they initially say the negative way, oh no, it will turn away. But because they think is if you rotate forward and backward with asymmetric rotor, then it will be a problem. Oh, thanks a lot. The question is on the top there. And in this case, the important thing, when you have asymmetric rotor, you rotate forward will be better than rotate backwards. But in this case, only minor difference there. Most importantly, in my personal opinion, electric vehicle, most of the time you drive forward. Tell me, when are you going to reverse the car? In parking, in the garage, yeah, something like that. Very occasionally use that. So that's why I strongly believe this type of technology will be excellent for electric vehicle. Okay, I don't believe you're going to reverse your car in the motorway you're driving. Yeah, that would be really dangerous. Okay. Shall we pick up another one? How about this one? Paul Laho, is a field-oriented control for BLDC motor for man-powered vehicle application is better, and which method is better in field-oriented control, direct or indirect control. This is also quite interesting. I mean, the terminology here is very interesting. Called the BLDC, stands for brushless DC motor. Yeah, in the machine, permanent magnet machine, we very often divide it into brushless DC or brushless AC. But for brushless AC, we very often call it permanent magnet synchronous machine, like exactly as the previous question. Okay, but their difference mainly is in the motor design and the control. So for the motor design, for brush AC design, it is desirable to design the voltage, induce the voltage as a sinusoidal. Then in brush DC, we prefer design as more square or trapezoidal one. That's one desirable. Then if you try to control that, for brush DC motor, very often is 120-degree square waveform. Then for brush AC, we inject the sinusoidal one. So this is a major difference. Yeah, of course, there's some difference in the position sensing as well. I think it depends on the application. If usually brush AC or permanent magnet synchronous machine type, the performance is higher, and also quality is higher as well. This is why in electric vehicle, all of them are using brush AC or permanent magnet synchronous machine. None of them is brush DC machine. It is important to consider the torque density or the power level, because when you have high torque density, high power level, brush DC got the time harmonics there. That will cause a lot of losses, particularly in the magnet. Then magnet usually is in the rotor is quite poor for heat dissipation. It could cause demagnetization in that case. Yeah. So my opinion is if for high quality one, and then maybe need to use brush AC or permanent magnet synchronous machine, and also employ vector control is more popular at the moment, but direct control is also fine. That's related with the direct or indirect control. I hope I answered this question. So in my opinion, essentially there's no major difference, just a bit different in the voltage and the current. But important this is for high torque density is about the current harmonics, which could cause additional loss, cause heat demagnetize the magnet. If we demagnetize the magnet, there will be disaster. Okay. Okay. So next one. I think the next one is a very similar one to Bo mentioned. I think I will skip that one. Is okay? Yeah. Can you suggest the research topic in that field? I think I'll talk about that later. Research topic is far too many there. Is okay. And our next one is not comment. I could that. And can you perhaps give insight on the future of non-magnet wonder field machines in the industry, especially considering their low efficiency performance? I think that one is interesting, because this one essentially is Akilo's second question. And this one essentially, is showing a lot of people working on a non-magnet type of machine, and are actually also heavily involved as well. This type of machine, I would like to say, first of all, it depends on the design. In general, the torque density or the size of the machine for the same power cannot compete with the permanent magnet machine at all. However, we need to consider that in the permanent magnet machine, as just a previous question asked about the winding topology as well. And then for winding topology, very often for the permanent magnet synchronous machine, it needs to be distributed, like the Toyota Prius one, the photo I just showed. Then that machine has relatively long end winding. Then the one you're talking about, the wonder field machine, and the end winding could be very short. Therefore, within the same space envelope, you can try to extend the effective part which produces torque. Then you can get that relatively low torque density of this motor technology back a bit, and then to make it matchable almost to the permanent magnet type of machine. And I have done the comparative study, and in fact, the torque is quite close. Power is actually even better. The power capability is even better because you're using the wind field. You don't need to use the high-speed flux weakening. And in fact, the efficiency also is quite good. And the maximum efficiency can be very high as well. But important thing is here do have one challenge there. Because the maximum efficiency is similar. But when you try to look at that, as I mentioned, the most frequently operated region for the electric vehicle, then it's at the low torque and also the low speed. Now, in that region, this wind field machine, the efficiency is much lower than the permanent magnet machine. Okay? And otherwise, it's fine. And I hope in the future, there's no problem with the battery. And then I hope before that, we should have enough layers magnet. Okay, let's have a look at this. I think that's all in the comments there.
The research project.
Yeah, then other part is not a technical question. Okay.
Thank you so much, Professor.
Well, thank you.
So I think we can end the session now. So
Yeah,
I request.
I would like to say thank you, and first of all for your organization by IEEE Energy Power and Energy Society, as well as the Industrial Application Society, and particularly to you, Study, and also Bo. And also I would like to thank everybody who is listening to my presentation. And well, without you listening there, I'm only just facing a screen. So I know you're all listening, and that makes me very excited. Thank you very much for attending.
Thank you, sir. Thank you. Thank you so much.
Thank you.